8.3 dot products and vector projections. So suppose we have two vectors A and B which are related as depicted below. If the light shines on A, it will then cast its shadow on B. This is also called the projection of A onto B. The product of the magnitude of this projection and the magnitude of B is called the dot product. So literally what this looks like is A, vector A, dot, vector B. So it's different than just multiplying, it's the dot product. So where you use dot products is to find how parallel two things are. More or less, you're taking the parallel components. So you have two vectors, right? So you look at your first vector, and then you want the part of the second vector that's parallel to the first. So clearly you can see A is not perfectly parallel to B. But if I took the x component, that would be the parallel portion to B. Okay, so so how do we do this? So I have two vectors. So vector 1 is A, vector 2 is B. So if I take A1 times B1 and then add it to the multiplication of A2 times B2, that will be your dot product. So when you take a dot product, you'll get one answer, one single answer. So it's just, more or less, it's a formulaic way to find. Can you not, touch other people? Thank you. Get out your notes, pay attention. Okay, if you're going to be distracting, I'm going to send you out. So, dot product of vectors in a plane. Alright, so if an angle between two vectors is 90 degrees, then none of the vector A can cast a shadow on B. Okay, so this is what happens this is what happened 6 days ago. 6 days ago was March 21st. Anything special on that day? First day of spring. AKA it's a equinox, right? 12 hours, so like 23.5 degrees latitude. If you were there, the sun would be directly ahead.
Right on top of 90 degrees.
Actually, it's when you're over the equator. When you're over the equator, there's 12 hours of daylight, 12 hours of...
below tropics.
Yeah, okay. Anyway, my point being, if you're staying on the equator 6 days ago, on the equinox, you'd have 12 hours of daylight, 12 hours of night, and at noon on the equinox, if you're staying on the equator, the sun's right above you. Have you guys ever seen a picture of anything? The sun is straight down, so where's your shadow if you're standing right under the sun?
You don't have a shadow.
You don't have a shadow. Literally, there's not a shadow on any side of you because the sun's right above of you. So there's not a shadow shining on either side. So this is what I'm talking about when the angle between the two vectors is 90 degrees. So the sun is shining straight down on you. You are 90 degrees from the floor. You are orthogonal from the floor. You are perpendicular. You are normal from the floor. You're 90 degrees. Orthogonal. Orthogonal means perpendicular.
Are there people that...
So my point is, hold on. The point is, if you have two vectors and they are 90 degrees, their dot product is going to be 0. Because remember how I said I'm looking how much of it is parallel to each other? Something is perpendicular. None of it is parallel to each other. So if your dot product is 0, you're perpendicular. You're orthogonal. So repeat after me. Orthogonal.
Orthogonal.
Orthogonal. Orthogonal. Orthogonal. So what does this mean?
It means that when you have two 90-degree angles, they meet at a certain point and it's orthogonal.
No, it means perpendicular. There's literally one 90-degree angle and it's between the two vectors. So on the test, if you cannot ask me, what does orthogonal mean? I will not answer.
Perpendicular.
Oh man, it means perpendicular. Orthogonal means perpendicular. It's a new vocab word, and we're going to incorporate it into multiple parts of this lesson.
So Brian.
So if you find the dot product of two vectors that are orthogonal, it's going to be 0. How do you know something's orthogonal? The dot product 0. Or it's drawn and they're 90 degrees between each other. Yes, sir.
So it's when you have two vectors forming a 90-degree angle.
Yep. I understand why that's funny, but okay. Nathan?
So are there people that go to countries or just anywhere on the equator and just for the equinox just to stand there to see the shadow?
Why would someone do that?
Well, people go travel just to see the eclipse.
That's different.
Didn't
Have you?
see the eclipse?
Debatable. I mean, I've never not had a shadow standing out in the sun.
It's not that you don't have a shadow. It's literally the shadow is like
It would be
right
kinda under you. It's under your feet.
It's literally under you.
It's like how this
Oh,
is.
yeah.
When you have a light shining down on you.
It's like right now. Right now the shadow's under my hand because the light's right above.
Well, it's still pretty cool.
So it's orthogonal.
So
Yeah, but you still do have a shadow in there.
okay, I didn't say you don't have a shadow. It's just the shadow's not an angle. During the equinox, if you're at the equator, it's not that you don't have a shadow. It's literally, it's directly under you. No part of it is at an angle.
Yeah.
Okay.
Yeah, really expensive.
Are we playing word association? I thought this was math. Cool.
Daddy goes to equinox, guys.
Why is the gym called equinox?
It sounds.
Are we ready to like go on with the lesson? I'm glad we're screencasting this nonsense for yeah, I did this so I don't waste my own personal time making screencasts that people don't watch. If they don't want the screencast, cool. Dig through the shenanigans you guys pull. Cool. So if I want to do the dot product of u and v,
You do -3, 4.
so -3 times 3. Take the first one's multiplied, add it to the second one, so times 4 plus 6. So this is going to be -9 plus 24. So the dot product is going to be 15. So it's not orthogonal. If it was orthogonal, what would the dot product be? 0. Orthogonal means perpendicular. Okay. If two vectors are orthogonal, they are perpendicular from each other. Cool. In physics, you use dot product a lot. All right. Theoretically. Okay, B. All right, let's do this. So, U dot V. This is going to be 2 times -14 plus 7 times 4. These, the first one's multiplied, the second one's multiplied together. So we have -28 plus 28, that's equal to 0. So if the dot product's 0, they're going to be orthogonal. Orthogonal means perpendicular. Okay. So let's go through the properties of dot product. Okay, commutative property. If I say 2 times 3, it's the same thing as saying 3 times 2, right? You get 6 either way. The order you multiply doesn't matter. You can take the dot product of u times v, of uv, or you can take the dot product of v and u. The order doesn't matter. You get the same thing.
Mr. O'Brien, so why are you like crisscrossing the numbers?
Because this is the way you do dot product. If I come up here, do you see how the first item of both, you multiply and add them? And you also have the second, multiply and add them.
Because if it's in a line, like, wouldn't you think it's like A1, A2?
But that's not how dot product works. You have to look at the dot product, like, formula, dot product, way you do it. Yep. Cool. Okay. So let's go through the properties of dot product. So commutative property, the way I do the dot product, it shouldn't matter if I do u dot v or v dot u, you get the same thing. The distributive property, either you can do the dot product after you add the two vectors, or you could take the dot product of each of the vectors with your vector in question. So this is like, something to keep in mind. This would be good when you're going through problems. Scalar multiplication, either you can do the dot product, then multiply, or you only really need to multiply one of them. Because doing a dot product, you're basically multiplying things together. So if you're multiplying 3 numbers, you only multiply one of them. What's wrong? I don't know why people are looking over there. Okay, what's your question?
I don't understand.
Okay? So either you can multiply the scalar times your dot product, or you can multiply it by the first and do the dot, or multiply by the second and do the dot. It's a lot of theory, honestly. You just have to work some problems. So you'll see the level of what I want when we go through some homework problems. If you do a dot product with a 0 vector, you get 0. And then dot product and vector magnitude. So if you take a dot product of a vector times itself, so I'm going to do an example here. For example, if the vector u is 4, 2, and so if I do the dot product of itself, u dot u, this is going to be 4 times 4 plus 2 times 2. So I see that this is 4 squared plus 4. Sorry, times 2 squared. Interesting. So, add these together. This kind of looks like a squared plus b squared, right? Pythagorean theorem. So that's why this is equal to the magnitude squared. So if I want to find the magnitude, literally, I would do the square root of the dot product. So that's what I'm talking about down here, as I'm showing you this example, a little further detail. Yep. Do we need more time to write this down? Okay, so now we're going to use the dot product to find the magnitude of vector A. Magnitude is just a length. It's the resultant. It is literally your hypotenuse. Oh yeah, Emma, this is for you. I don't know when you got in here. This is sneaky, sneaky. Okay, so if I want to find the magnitude of vector A, how would I go about that? So it would be let's do it our new way. Square root of the dot product. So the dot product is going to be -6 times -6 plus 5 times 5, because that right there is the dot product of A with itself. So that's going to be 36 plus 25. So that's just square root of 61. So this matches what we've done before, because before when we were trying to find the magnitude, sorry, this should be A. Before when we were trying to find the magnitude of A, we would do square root of x squared plus y squared, so we get the same answer. Cool. Okay. And it kind of makes sense, because imagine you're laying on the ground. Now think about the shadow underneath you. How does your vector compare to the vector underneath you? They're literally the same thing. They're pointing in the same direction. They're 100% in the same direction. Where? Here?
No,
Oh, wait. Not up. You wanted me to only go a little up.
no. I want to see the writing. I can see it this way.
Okay. It's coming. Okay. Like that?
Yeah.
That's right. Okay, so cool.
So you can do any of these properties? No?
I don't understand the question you're asking. What do you mean you can do any of these properties? These are the properties.
Okay.
Okay. Alright, the angle between two vectors. Yeah.
So why are we doing -6 times -6? Is that what the dot product is?
-6 times, yeah, because you're doing, I'll show you.
If we had two,
So if I add, so you'd be doing -6 times -6, which is right here. And then you would be doing 5 times 5.
The magnitude. So if we have
So you're finding the length of the parallel portion. And if they're 100% parallel to each other, literally the whole magnitude, the amount that's the amount that's shared between them is the whole thing. So it's going to be the full magnitude of your vector.
So if we had two separate vectors, like if, you know, a separate vector b, which was like -3, 5, then would it be square root -6 times -3? Yeah.
Yep.
Okay.
All right, so the angle between two vectors, yeah, so the dot product literally is telling you like how much of the x component, right, the part that's parallel. So for instance here, like here's my vector b. Why is this not working now? So here's my vector b. Then I have this vector a. So I want to know how much of a is actually parallel to b. So it's going to be this length. Literally, it's going to be the x component of a. That's the length that is going to be parallel to b. We're looking at the parallel portion, right? So dot products are about like parallel. So this is really getting into like theory and you understanding like really what dot product is.
You're not finding hypotenuse?
No.
But it's kind of the same.
So imagine if my two vectors were the exact same length. Okay, well how much of it is parallel? Literally the whole length of the vector. So that's why I could find, if you do dot product with itself, you're going to find the actual length of the vector, the magnitude of the vector.
Exactly parallel, what answer we get?
You're going to get, no, you're going to get the full length of the original vector. 0 is perpendicular. If you get the full magnitude of the vector, they're 100% parallel, and then you're going to have all in between. Yeah. Dot product's a measure of like parallelism. So, yeah, it's interesting, but if you're like, I have no idea what you're talking about when you're dealing with angles, then it's hard to describe that to you. Cool. So let's derive a formula for the dot product of a and b. So literally, what I'm doing is I want the length of the projection, length of the projection b on a, and then I'm going to be multiplying it by the magnitude of b. So where this comes into play, let's think, what is this length actually? If I want to find the length of the projection of b on a, aka the amount of b that's parallel to a, aka the x component, how would I find the x component?
Cosine?
Yeah, I'm going to do cosine. So if I wanted to find the x component, that's going to be equal to the hypotenuse times cosine of your angle. Okay, so I can rewrite this line as a dot b, vector a dot vector b, is going to be absolute magnitude of a, which was the hypotenuse, times cosine theta, theta is the angle between our two vectors, times the absolute magnitude of b. Alright, and so this comes from the fact that cosine of theta is equal to this projection of b on a over
And then just multiply that times
A.
b. Whatever b is.
so if we multiply it by b, we will,
Yeah.
what is that?
That's included in the formula, multiplied by b.
Yeah, so the final formula is a dot b is equal to absolute magnitude of a times the absolute magnitude of b times cosine of the angle between them. Normally I don't derive formulas for you, but maybe you understand this one. And if I wanted to get cosine by itself, cosine of the angle between the vectors is just the dot product of the vectors over the respective multiplication of their magnitudes.
But does B include just projection B of A? Or does
No, B is literally the magnitude of vector B.
Okay.
Yep.
I don't get where you get the volume. What is the absolute value lines mean?
The absolute value lines mean like magnitude. So, because I don't want the top is the dot product of A and B. So. Okay, and then while I was here, I derived this lovely formula for you right up here. Hopefully you can see that. Okay. We're doing good, we're doing good. Alright, so this is how you can find the angle between two vectors. So what we've been doing so far is like, I give you a vector with an angle, or I give you the components, the x and y components. If I have the x and y components, you can find the resultant vector and the angle, the direction it's going. What if I have two vectors and I want the angle between them? You can use dot product. So in our next example, I showed you how to find the angle between two vectors, right? I proved how to find that guy. So if theta is the angle between two non-zero vectors, then cosine of the angle between them is equal to their dot product, u dot v over absolute magnitude of u times absolute magnitude of v. Okay, so let's break this down step by step. Let's find out what the dot product is.
The dot product is on top of the.
So it's going to be 1 times 2 plus negative 4 times 6. Does that answer your question? This is the dot product. So that's 2 plus 24, so that's negative 22. Absolute magnitude of u. Actually, let's do v first. Let's do v first. What? Yep, negative 22. Let's do absolute magnitude of v first. So it's going to be square root of 2 squared plus 6 squared. So that's square root of 40. So that's that guy. It's x squared plus y squared. Right there.
Oh.
Yeah. Cool.
Should we simplify this?
Honestly, it doesn't matter. It doesn't really matter. Alright, so let's find the magnitude of u. Square root of 1 squared plus negative 4 squared, so that's square root of 17. So that's what goes right here. So I found each piece independently. So I have negative 22 over, okay, if I'm taking square root 17 times square root 40, I'm just going to simplify and do square root of 17 times 40. And of course, I'm going to be doing cosine inverse of this whole thing because I'm trying to solve for an angle. I'm solving for an angle. You use cosine inverse when you're solving for an angle. Okay. So I'll pause here, make sure we're doing all right. We'll draw a picture.
Should we remember that formula?
6 which one?
Cosine the unit u times v over square over the absolute value of u times v.
Yeah. I'm not going to give it to you. Okay, so I'm going to draw my two vectors. My first vector has negative 4, y, and 1, x, so it goes to here. So that's vector u. My other vector, maybe make that, I'll make it darker. I'm drawing this so you can see it. Okay, So there's vector 1, that's vector u, so I'm drawing the two vectors. I have another vector, vector v, that goes 6 up, because it has 6 in the y direction, 2 in the x, so it goes somewhere like that. Alright, so that's vector v, so you can see my two vectors. There we go. And what we were trying to find was the angle between them. So I was trying to find what this angle was between them. And I found that was 147.6 degrees. So that's how you find the angle between them. Okay, so visually maybe that helps a little bit. Kind of. Well, there was an easier way to find the bonus question. You just have to draw a picture. I'm trying to think, did everyone take it? Who missed it? Who missed taking it today?
Oh, I did.
You finished though.
Yeah.
No,
I took it too. I think
you,
everyone finished.
did you show up? Okay.
Yeah.
Oh yeah, can I ask you?
I'm trying to think. Who did not take it? No, everyone did. Okay, cool.
Okay, wait, what's the book?
So the first bonus question
Was it
here's
0?
yeah.
Yes!
1, 2, 3, 4, 1, 2, 3. Okay, ready? Here was the first vector. The first vector. Here's the first vector.
Oh, it was the one that you crossed out on the practice books.
Yeah. I learned how to do that one. So
It's not cheating.
I'm not sure the thing. I got
Wait, what's cheating?
It's not cheating. Yeah, it was only 1 point. So this was literally what's the angle between them? Whatever. Okay. Well, you know what? Why don't we just do a live? We'll do a live. Okay. So vector 1. What was vector? Vector 1 was like v1, v2. And vector 2 was, or did I name it like a?
no 4 times.
And u was 4 times. Yeah.
What was the question? What did it do?
What's the angle between it?
Nothing. It's the same.
So the way I drew it, the way I just drew it, like you could have figured out. You could have figured out it was that. So the angle between it is going to be the dot product. So this is 4v1 squared plus 4v2 squared over magnitude of a over magnitude of b. Oh my god. So square root v1 squared plus v2 times square root of 16v1 squared plus 16v2 squared. Okay, this is running out of room, and I don't want to make sure we finish the lesson. Just want me to put it on the notes so you can see it later. Okay. Cool. Okay. Anyway, that's like one way you could do it. Or you could just draw like, oh, if this is the first vector, and it's literally 4 times the length. It's going to be the same thing. Okay. So let's finish. I think we have no time. We can finish the lesson. Projection of A on B. Recall from the previous example that the projection of A on B can be written as projection of A on B. So that's going to be, I don't know how to describe this. Dot product of A and B over the absolute magnitude of B. So the expression is only the magnitude of the projection. So it's only the length that is parallel. It's not giving you the direction. In order to be, it's not necessarily that, to make sure it's going in the same direction as B, it's not just like the parallel. Okay, to have parallel lines, literally when you drive on the interstate, when you drive on the freeway, the cars coming at you are parallel to you, but they're not necessarily going the same direction. So you can have 2 cars going that way, or you can have a car going forward and one going backwards. They're still like parallel, still 180. They're still going along the same line. But I want to know, like, how do I actually get them to go the same direction? It's like a party up in here. Let's see. Cool. I should probably like update these so you guys know your participation grades. I should do that. But also, I have so much to do. What? What'd you say? So I thought.
Disgusting.
I've
Disgusting.
gone to the bathroom once in a while.
Since yesterday, when you went twice.
The test ended. You said we could go outside.
I said you guys should work on your final for senior stuff.
No, you said we could leave.
Oh,
Who told you we could leave?
You and Jenna left early.
You said we could.
I don't remember this.
You said we could leave. We left at like 2:13.
Alright. Smart move. Keep fighting me. Alright. I need to. I need to update all your grades. This expression is only the magnitude of the projection. In order to give it the same direction as b, it's necessary to multiply by the dot product of ab over the magnitude of b by the unit vector of b, aka the unit vector will give it the same direction. I want to go in the same direction of b. I don't want to go opposite directions. I want to go in the same direction. So we learned how to do a unit vector. So when I multiply by the unit vector, it just turns into the dot product of a times b all over the magnitude of b squared times the vector b.
Was the bottom formula of the finished formula?
Yeah. Yeah, I don't remember this yesterday. I don't remember it at all.
Why is it doing that?
I don't know.
I colored it by itself.
Oh yeah, I don't know why this delay is so slow.
I think it was like leaking and then it just
No,
filled in the
not at all. Find the projection of u onto v. So find the projection of u onto v. Okay, so keep in mind that this was the unit vector. And we also, this first part is the magnitude, so I'm literally taking the magnitude times the unit vector. So what this part in blue does, it's going to be the full projection vector with magnitude and direction. So this last part that I colored in blue is going to be the full projection vector with magnitude and direction. I feel like I'm like ready to get married because I'm really good at not listening to people, and so like selective hearing is definitely a trait I have now. Yeah, it's rough. Like I was meeting with a student yesterday, and I know like 7 people came out to me and like said something to me. I have no idea because I was focused on the student I was trying to help. That was not you. You were not the person I was helping. It was E period yesterday. I was upstairs at the tables.
Oh, I was there.
I know like 7 people came up to me. I have no idea. Like, school, just like when I'm focused on something, cool, I have selective hearing. Of course I'll be like, yeah, you can go. No, you're here the whole time. Yeah. Probably. Did you say something? What did you say to me? I don't remember.
I said that I'm leaving early, but I don't know.
Okay. Right. I don't know. I knew 7 people came to me. I just was like, why are you bothering me? I'm trying to help this child. There were no rooms open.
I thought it was a screen test.
Whatever. Cool. Alright, let's do the dot product. Dot product of u and v. Yeah, well, I'm not taking my personal time to do them anymore, so. Cool. -4 plus 30. It's going to be 26. Alright, I have the dot product. Because really what we're going to be doing here is we want the projection of, let's see, of u onto v. So I'm going onto v and it's going to be the projection of u. Okay, so I'm going to do the dot product of v and u all over the magnitude of v squared times the vector v. So this is how you know like where things go. Whatever you're trying to project onto is going to be like the b here in our question. So I need the magnitude of v. So it's just going to be square root of 4 squared plus 6 squared. 36 plus 16 is going to be square root of 52. Alright, so if I go ahead, plug this all in, I have 26 over square root 52 squared times the vector 4 comma 6. So 26 over 52, right, because the squared and the square root cancel out. So 26 over 52, 4 comma 6, that's the same thing as 1/2 times the vector 4 comma 6. So the projection of V onto U is going to equal 2 comma 3. And I'm going to call that vector W, because U, V, W, it's the next one in line. There we go. Excelente! So, the other part, write U as a sum of two orthogonal vectors, because I made it equal a new vector. Yep. The projection I'm labeling as vector W. Because I had vector U, V, and if you follow the alphabet, U, V, W is the next one. That'd be nice. I get so distracted. What? What's your question?
Where'd you get 2?
What's half of 4? Half of 6? Cool. That's where it came from. Well, scalar multiplication of a vector.
Oh, that's scalar multiplication.
Well,
Distributed.
that was scalar multiplication, that wasn't dot product. Coolio. Okay. Write U as the sum of two orthogonal vectors, one of which is the projection of U onto V, aka that's my vector W. Need something to share? Okay, then you need to make sure you take notes. Alright, so what I'm trying to do is write this as a sum of two orthogonal vectors. So I have vector U is going to be equal to vector W plus vector Z. What the hell is this vector Z? I don't know. We're going to solve for it because it said one of the two vectors had to be my projection. So let's see what it is. My vector U is 1 comma negative 5. My vector W is 2 comma 3. And let's go ahead, let's solve for what this vector Z would be. So this is vector W is 2 comma 3. Vector U is 1 comma negative 5. This is part B of the same problem. Part B. We got this. Alright. Yep, it's fine. Alright, so if I want to subtract my W vector from both sides, so I have 1 comma negative 5 minus 2 comma 3. That's my vector Z. Oh, is it supposed to be a negative 1? Is U a negative 1? Yeah, it is. My bad. There should be a negative 1 right there. Where? Oh, it was supposed to be negative 1 comma 5. Oh, I put the negative in the wrong place. What's wrong with me? Okay. Because I wrote U as the sum of two orthogonal vectors, aka these two vectors have to be perpendicular to each other. But one of the vectors has to be U and V. Okay, so I took my original vector U, and I know it has to be a sum of two vectors. One of my vectors is the projection. So I said, okay, my last vector I'm going to name Z, and I got to solve for it. There, solve for it. It is. I did write it. Right here, U is the sum. Where what? Z, because that's the vector I have to solve for. Because I know one of my vectors has to be the projection. The other one, I have no clue what it is, and I have to solve for it. Because I know what my original vector is, and I know what my Yeah, I know what my projection vector is. Okay, so we're going to do the last problem, and then this will be it, because I already gave you guys the homework I handed out. So example 6, 5, a person pushes a box with a constant force of 40 newtons at a constant angle of 45 degrees. So this is going to be, the vector is 40, this is 45 degrees. So we want to, find the work done in joules to move the box 12 meters. Okay, so I know what my distance is. So I'm trying to move it 12 meters. I'm going to be using a little physics. Work is equal to force times distance. Work is literally the dot product of force and distance because they have to be parallel. You're taking the parallel component of force. So that's what you do when you do dot product. Surprise, physics time. So my force, well, I can break this down into components. So you just do magnitude times cosine of your angle, comma, magnitude sine of your angle. The distance, well, I know I'm going 12 meters, and that's going to be horizontal, not vertical. So if I do the dot product, I'm literally going to take 40 cosine 45 times 12 plus 40 sine 45 times 0. Oh my god, the y component cancels out. Who would have thought that the force and the x component, the only parts that are parallel to each other, will actually give me a number? So this is 339.4 Newton meters. You might have learned that in physics. This is the same thing as saying 339.4 joules. Cool, and then that's it. That's the end of our lesson. Seniors, you're done learning new stuff.